So we've been presented with a compound and been told it contains carbon, hydrogen and oxygen, and we've been asked to work out the empirical formula. And in terms of the percentage compositions by mass, we've been given that it contains 50% carbon, 5.56% hydrogen and 44.44% oxygen. The first thing I'm going to do is I'm going to take a quick look at, well, if we add up all of these percentages, what do we get? Do we get 100 or do we get something else? So I'm just going to go through that, and I mean, by visual inspection you could probably figure out what it's going to be, but nonetheless going to do the calculation. Yeah, that should be a 44 point, yeah. Okay, so have a go, see what you get, and if you did that, you should find that that does come to 100, right? Now, in solving this, which, as you know, we're trying to solve here for the empirical formula, we need to find the simplest whole number ratio between the elements in this compound. So what we're going to do to solve for this is we're going to make an assumption, and that assumption will enable us to actually do some moles calculations, etc. on this information. The assumption I'm going to make is that I'm going to assume that the sample, the size of that sample by mass is 100 grams, and given that these percentages of the elements are also by mass, therefore it enables us to say, well, therefore this would be, for example, 50% would be 50 grams, right? 50 grams and so on and so on. So this is going to be carbon, right? So carbon 50 grams, hydrogen 5.56 grams, and so on, right? So oxygen 44.44 grams. Now what we're going to do is we've got masses, but obviously with these elements we've got different relative atomic masses, and hence we've got different we've got different molar masses basically. So because of that, these elements are not easy to compare in terms of amounts of substance in their current form. We need to convert it into a form where it's easier to compare it. So we're going to use the equation that the moles N is equal to the mass in grams divided by molar mass. That's in grams per mole, and using that we need to divide these by their respective molar masses. Now you may know what the molar masses for these are, however, let's say you didn't know, or if you don't know, we would simply just need to refer to the periodic table to figure that out. So okay, so here what we can see is we've got 12 for carbon, right? So carbon, hydrogen, we've got 1, oxygen, we've got 16, right? So therefore we can say, okay, well, and just put this here as well. So for the molar, so this is just more or less to show my working, right? So it's just showing my reasoning in writing. So MR would be MR of carbon, that's 12. MR of hydrogen, it's going to be 1. MR of oxygen, that's going to be 16, right? Okay, so now we've got the molar masses. We're simply going to divide these by their respective molar masses, right? So 50, we're going to divide this by 12, divide this by 1, divide this by 16, right? And having done that, what do we get? Well, we're going to get here, we're going to get and I'm gonna actually do these to 5 decimal places. So at this point I would encourage you, if you want, you can have a go, see what you get when you calculate these. But if we do run that calculation, what you should find is you get for the moles now. So for carbon, this is going to give us 4.1667, right? And for hydrogen, well, we're dividing by 1, so it's not really going to change it. It's just going to get 5.56, right? And for oxygen, so if you do that, we would get 2.7775. At this stage, looking at these numbers, what's obvious is that they don't easily round to a whole number. Remember, we're looking for the simplest whole number ratio. Any of these given values, if we round it to 2 decimal places or to 1 decimal place, we don't get a whole number. So to achieve our first whole number, we'll look at the smallest value we've got among these, divide every value by the smallest number, and then we would get at least one whole number, which will be 1, right? So in this case, we can see that the smallest is the molar value associated with oxygen, right? So therefore, we're simply going to divide all 3 of these by 2.7775, right? And what does that give us, right? So you can have a go and see what you get when you do those divisions. But if you do that, what you should find is you get 1 so this is for the oxygen case. I mean, for the carbon case. For carbon, you're going to get 1.99990, right? And then if we look at the case for hydrogen, you should find you get 2.00180. And in this oxygen case, we are simply dividing we're dividing the same thing by itself, so we're just going to get 1, right? Okay, so when you look at these numbers, what do you notice about them? When you look at them from a 1 decimal place, rounded to 1 decimal place, rounded to 2 decimal places, what do you notice about them? Well, when I look at these values, I can see that these two are very close. This one's already a whole number, as we discussed. This is, we're expecting that. But here, if we round any of these to 2 decimal places, we get an integer value. So in this case, we get effectively 2.00. In this case, we get 2.00. And to 1 decimal place, of course, it's the same. We get 2. So based on that, we know that, okay, well, the values that are going to be associated with carbon, because this is effectively our simplest whole number ratio. I mean, 2 and 1, it's not something you can necessarily divide it by that's going to give you a different number that is still a whole number, right? So so if you divided 2 by 2, you might get 1, but the problem would then be that dividing this 1 by the same, which you would have to do, is going to give you 0.5, and then you don't have a whole number ratio. So okay, so anyway, this would be C2, right? Hydrogen, you've got H2, and oxygen, we've got O, and then, well, I mean, you could say O1, but we will refine that as we get to our answer. And based on that, we can say, okay, well, the empirical formula would be C2H2O, right? So this, in this instance, this actually would be what our empirical formula is. And actually, although this is an empirical formula, if we looked at it from a perspective of it being a molecular formula, there's actually a quite an important chemical compound that has that molecular formula, right? And it's called ethanone, right? And this is the structure. So I mean, I've put the name here. You can look this up and try and learn a bit about what reactions it can be used for to produce other things, of which there's many reactions, and yeah, so we've got effectively, as we discussed, it was C2H2O, and you can see you've got 1, 2, C2, H2, H2O, right? Okay, so yeah, that's our empirical formula in this case.